So it says we're live, right?
Yeah, I need to turn the camera around.
So it says we're live, right?
Yeah, I need to turn the camera around.
So it says we're live, right?
So you come out.
What is that noise that we're getting?
Feedback because we're both logged in.
Okay, so
She's coming out.
okay, got it.
It sounded like someone was conjuring a demon.
Okay, I'm gonna go see if I can get the link and look.
Okay.
So the slides don't really.
Oh, you can turn the light on.
Yeah, let's see if we can move like this. Still not easy to see there. Just trying to see if we can. Oh no. So what are you trying to do?
Oh, I'm trying to make this one taller.
I think you
That is
should.
too wide.
Is there? What is the problem?
Oh yeah, so there was one mode that you had. I think it was make the figure larger. Does it make the whole screen larger?
I am, yeah.
But if you want to make it larger, you're gonna have to make it.
No, there was actually one mode where it almost the full screen.
Cool, what do you have to do these days?
Yeah.
This one?
Yeah.
Thank you.
Okay, this one. And now it
Oh,
actually.
I've heard they're actually doing really cool stuff.
We're working on electrifying fleets.
Good to know.
I'm working on solar. So one of the
So now it does seem like it's.
renewable energy and energy efficiency. Kind of wondered some of the potential impacts of how do we integrate that forecasting.
Now let me just see if I can see it on mine, and then we should be good to go.
Cool.
You like working there?
Yeah, everyone did it without.
Yeah, I heard good things about really most communities.
Hey, how are you?
you?
Is this your status, I guess, gives benefits and drawbacks?
I think it's gonna be like so these are things that are it's all about authority and regulatory stuff is right.
Oh, but it's not far enough.
You can hear it. Okay, very clear.
So then we need to be in good shape.
You're our test subject on the live stream.
Thank you so much, buddy.
I should recommend our center to have this too.
No, this is it's 2019, so they should know, that's what I always keep telling is that in this day and age, we all should be doing this. Everybody should be able to see these great events, whether they're in Africa or China or anywhere. That's fine. So we'll just wait a few minutes.
How are you liking SAIS so far?
I love it. I'm ready for summer to come around now. We'll break from classes.
Yeah.
But overall, I feel like it's a good choice.
Where you're gonna be or where you're gonna be this summer.
Well, this summer, yeah, I'm gonna be doing transportation stuff for a nonprofit. We're looking at declining ridership in so trying to get some great costs, especially with Amazon coming in.
I think I've seen you.
Making sure that those people don't start just driving everywhere.
Okay, so since I said it at 12:30, August beginning, that people should see.
That's good.
Okay.
I never heard of them, but I.
She can hear it, but she's in the back.
Did you have anything about this?
Yeah, she was, yeah, I checked out.
Yeah, so I'm working on that.
So whether you're going.
Yeah, so.
Yeah, I remember the transportation was
Should be fine. I will be talking.
So reduction in revenue and energy efficiency.
I guess my
The go-to topics. But I wanted to be in urban planning as a kid. And I realized what urban planning is actually doing. So it kind of gives me
Wonderful.
a little bit of exposure to that.
I see the slides and everything.
So.
It's very important.
Yeah, I agree. Or actually, yeah. Yeah, I know. I'm writing one of my classes right now, the electronic related testing. It's such an economic no-brainer. In New York. I have not seen the latest. Last I heard, De Blasio was trying to do it.
I think they passed.
Oh,
And the budget is to be below the 60th. Or it's sweeter.
when was this?
Recently.
Yeah.
A couple days ago.
Yeah. Oh, shit.
I don't know, there's some masters students.
Yeah.
We
I only have one PhD.
From DC,
Oh, I know. It's such an obvious case.
that like, if we were to propose it, Congress would like override it because members from Virginia and Maryland
It is
want
it.
their jurisdiction and not,
Yeah, but at any given time, about 100 students.
Central would
How
still
many
be.
of them are energy environment?
So that's
I know that.
the energy program. The school as a whole is 1,000 students. It's still smaller than some of the others, like SIPA, for example, it's 1,000
Yeah.
students.
Okay.
And we also have some of them are in Bologna on our European campus, and there's a small group also in China. But most of them are here.
So.
100 energy environment students.
Yep. So we take about 50 a year, but they don't. They apply directly to the school, and then they can figure out the concentrations.
Oh, so you
Okay,
need
so
to
it's
try
right
to.
here.
Yeah, roughly. That's it.
Okay.
So anyway, should we get started? If people trickle in, then that's totally fine.
Well, if you notice, like when they advertise college, they're never advertising content. The ads you see in like.
All right, everyone,
always-
thanks for coming.
Yeah.
Today is a big day for our program because this is the first time we are trying live streaming our events. The year is 2019, so we are about 10, 15 years behind where we should have been. But nonetheless, this is a major technological breakthrough, and it is a great pleasure to have Lucy Shiu from the School of Public Policy at the University of Maryland to inaugurate this new age here at SAIS, and she's going to tell us about some very exciting research on quantifying the rebound effects of distributed solar panel adoption. So Lucy will hear your talk, then after that I'll probably ask one or two questions myself and open it for the audience. Please, Lucy, take it away.
Yeah, I'm also okay with you interrupting me if you have any clarification questions. Thanks everyone for coming. This is a joint work with Matthew Kahn, who's actually joining Johns Hopkins very soon I think in June he's coming, but in the econ department. And then also Bo Xing, who is a senior analyst with a big electric utility company in Arizona. I think this is a good timing to present because this paper is currently revised and resubmitted at Journal of Environmental Economics and Management. So any feedback from you guys will be very helpful for us to prepare for the resubmission. And here I go. All right, so I will focus on my talk on residential sector today, and then if we have time in the end, I will also briefly talk about the results from the commercial or business electric customer. Okay, so as you probably all know, since you're Johns Hopkins energy environment students, basically distributed solar energy has been promoted by policymakers to reduce the reliance on fossil fuel and the associated carbon emissions and environmental damages. The penetration of distributed solar PV has increased a lot in the past few years due to the support from policies and financial incentives, as well as the decline of solar installation prices in the last few years. There have been many policy discussions centered around distributed solar panels. On the benefit side, it could potentially increase consumer surplus, and also bring potentially environmental benefit from reduced carbon emissions and also the associated environmental damage. However, it could also bring potentially negative impacts to the electric utilities. They need to collect sufficient revenues to cover their upfront costs in investing in the infrastructure such as transmission and distribution lines. In order to recover those costs, they have to collect sufficient revenues or they have to collect a demand charge. For distributed solar customers, they basically pay less to the utilities. That means reduced revenue for utility to recover their upfront costs. As a result, if there's no adequate demand charge, then in order to recover those upfront costs, electric utilities need to increase electricity prices for all of its customers, which will lead to the ongoing discussion about the distributional impact between the poor and the rich customers. Normally, it's the richer or higher income customers who adopt solar panels, and because they adopt solar panels, electricity price increase, then basically it's the poor customers that are subsidizing the rich customers to adopt solar panels. And the central part of this discussion is that the distributed solar customers, they reduce their bill payments to the electric utilities. So to adequately or accurately quantify that reduction of electricity needed from the grid is very important to design any new rate plans that can address the equity issues that I mentioned across non-solar customer, solar customer, and utilities. It is also very important to evaluate any potential benefits, such as environmental benefit, consumer surplus, and also for the accounting purpose of meeting renewable portfolio standards. So naturally, in order to calculate the reduction of electricity needed from the electricity grid, we can just use the amount of electricity generated by solar panels as a one-to-one replacement of basic electricity needed from the grid. And this is exactly what has been done in most of the integrated system models such as GCAM, and also in most of the existing economic impact evaluation studies. So the key thing that's missing from such approach, basically using solar electricity as one-to-one replacement of electricity from the grid, is that ignore behavior change. So when solar customers to consume solar electricity, basically which is free to them, it reduces the average electricity price that they pay for their electric utility company. So we all know that because of law of demand, when average price drops, then consumption will go up. This is what we call in our paper the solar rebound effect. The rebound effect is not a new idea, and it is widely discussed in the energy efficiency literature. For example, if you have a more energy efficient air conditioner, and you know it's more energy efficient, so you might use more of the AC by setting your temperature at a more comfortable level for a longer period of time. And that's called the rebound effect from energy efficiency, and it's been widely studied. But for distributed solar energy, there's no mention of solar rebound except for one study by Deng and Newton in their 2017 energy policy paper, which used quarterly electricity consumption data to analyze the rebound effect of gross metered solar customers in Australia. And in most of the solar literature, majority of them focus on the adoption decisions rather than energy consumption behavior after the adoption decision. Okay, so our paper, basically, we are the first to use high-frequency electricity data as well as the actual high-frequency solar generation data for each of the individual customers to quantify the solar rebound effects. I will mention later why such data set is important is because using high-frequency actual solar meter data can give us very nice exogenous variation for us to identify the causal impact of solar generation on consumers' behavior change. And also, we're the first paper to estimate the rebound effect of net meter solar customer. Net meter solar customer is different from gross meter customer, which was analyzed in the Deng and Newton paper. Basically, net meter customer, they first consume their electricity from solar panel, and if there's anything left, they can sell it back to the grid at any prices basically determined by each utility company. And then that is different from gross meter customer, which basically sell all of their electricity back to the grid. So for net meter customer, the causal mechanism for rebound effects is a price effect, versus for gross meter customer is the income effect. And then lastly, our paper is the first one that looked at solar rebound in the US. So we have three main research objectives. The first is how large is the rebound effect. And the second is to look at the heterogeneity, how different consumers may have different rebound effects and how those rebound effects are associated with their environmental ideology and some other factors. And then after we estimate the rebound effect, we evaluate more precisely the increase in consumer surplus and also the environment benefits from distributed solar power. Okay, so first I want to discuss our theoretical framework to motivate our research. And also, let me first define what rebound effects we're looking at. We're looking at microeconomic rebound effect. We're not looking at macroeconomic rebound effect, meaning the increased energy consumption due to increased economic growth from reduced electricity prices. So we're not considering macro effect. For micro effect, there are two types of rebound effect. The first is direct rebound effect. That means that is related to the example I just gave you about energy efficient AC. It's more efficient and use more of that AC. So direct rebound is only looking at specific appliances. And the indirect rebound effect is also related to other appliances. For example, if you know that you have more energy efficient AC, you may also use more of your dishwasher or your washers more, or your refrigerators more. That's basically an indirect rebound from other appliances. And for our study, we're looking at indirect rebound because we're looking at how the electricity consumption at household level instead of at individual appliance level. All right, so with those definitions in mind, here is a very straightforward those Econ 101 graph. So this graph shows you the relationship between what the price the consumers are perceiving, the average effective price, and the amount of electricity generated by solar panels. So for the utility company that we work with, the solar electricity is valued at retail rate. Is that the same rate as the consumers paying for the utility? So that gave us a very nice linear relationship, downward sloping curve between the average effective price and the amount of electricity generated by solar panels. And then the second graph shows you the very standard downward sloping demand curve. When effective price goes down, then consumers rebound. So they increase their gross consumption. And then we can assume certain price elasticity curve. Then finally, what we observe is the post-adoption total electricity consumption is a very nice linear relationship with electricity generated by solar panel. So basically, we are estimating how gross consumption changes with respect to electricity generated by solar panel. And that coefficient should be equal to price elasticity of demand, which is also equal to the solar rebound effects. All right, and then it is very important to look at how consumer surplus change if they actually have rebound effects due to a lower perceived average electricity price. Okay, so basically what we are proposing here is that the total change in consumer surplus is the value of those solar electricity valued at retail rate. So basically this part is original electricity price, retail price, multiplied by the amount of solar electricity. However, because consumers are perceiving a lower average price, because they know that solar electricity is free, so they think that, so they will instead rebound their electricity and increase their electricity. But instead, they're actually paying a higher price than what they're perceiving. So this is the price that they're perceiving, and this is the price that they're actually paying for those increased amount of electricity. So in the end, this part is the debt we lost due to the fact that the price perceived by the consumers is different from what they're actually paying. So as a result, the total change in consumer surplus or increase in consumer surplus is the value of solar electricity minus the debt we lost. So then we will empirically estimate the price elasticity or rebound effects of this curve, and then use the empirically estimated parameter to calculate what's the actual change in consumer surplus from solar panel adoption. So that's our theoretical framework. So next I'm going to talk about empirical analysis. All right, so where is our data come from? Our main data source comes from a electric utility in Phoenix metropolitan area in Arizona. And Arizona is a great case study for solar because currently its cumulative installed capacity of solar panels ranked third in the US. And also because there has been a lot of policy debate about pricing distributed solar panel in Arizona. So basically, there was one utility company who wanted to impose ban charge for its solar consumers, and that actually got a lawsuit of that electric utility company and a solar panel company. Okay, so there has been a lot of discussion going on in Arizona. And the utility company we work with is called Salt River Project. And then for Salt River Project, we have two phases of net metering policy. For the first phase of net metering policy, for the solar panels whose permit were applied for before December 2014, they were on the old net metering plan. So for that old net metering plan, there was no demand charge. And then the solar electricity was valued at retail rate, no matter it was directly consumed by the customers or it was sold back to the grid. And then for the solar panels whose permits were applied for after December 2014, they are on the new net metering plan. For the new net metering plan, there is demand charge, but then they have lower marginal electricity prices. And for our study, we're only focusing on the old net metering plan customers because there were very few customers that were on the new net metering plan. So basically, no demand charge in our sample. There are several data sets that we got from Salt River Project. The first one is a survey. It's a residential energy technology survey conducted in 2014, which gave us very detailed technical and socioeconomic characteristics of about 16,000 residential customers of their service territory. So it gave us very detailed information such as what type of AC they have, whether an energy efficient light bulb, refrigerator, solar panel, and so on. And then out of those 16,000 responses, there were about 277 solar customers. And then for each of the solar customers, we got the information of their hourly electricity generated by each of the solar customers. From 2013 to 2017, we also got the installation date and some of the technical and financial attributes of each individual solar panel. And then for all of the 16,000 customers, we also have their hourly electricity meter data, as well as their daily electricity consumption data. So before I show you the empirical analysis, let me first explain the important relationship between these different types of meter data. So basically now we have the meter data from solar panel, and then the amount of electricity that's directly delivered from the electricity company to the customer, and also the amount of electricity that's delivered back or that's sold back to the utility company from the customer. So the gross electricity consumption of a customer at any given day is equal to the amount of electricity that's delivered to the customer from the electric utility company, plus the amount of electricity generated by its solar panel, minus the amount of electricity that is sold back to the grid. Okay, so, and then for our main analysis, we're looking at how this gross consumption, instead of the electricity that's basically that they purchase from the grid. So we're looking at their gross consumption, how that changes with respect to the amount of electricity generated by solar panels. In terms of other data sets, in one of our heterogeneity analysis, we obtained the voter registration data from the county website. And then also, as I will mention later, it is very important to control temperature very flexibly. And then we obtain our hourly temperature data from NOAA. They have a publicly available database for hourly temperature. All right, so those are the data sources. Now, some of the descriptive statistics in terms of our sample. Here, the left-hand side figure shows you the distribution of per home solar panel system. On average, in Arizona, the average system size is about 6.6 kW, which is larger than the national average because Arizona, the land is cheaper. So the houses normally have larger roof, and then you can afford larger system sizes. In terms of yearly distribution, there is a gradual increase in average size over the past few years. Now, in terms of cost, so this is the cost without considering any financial incentives or financial subsidies. So per kW, the cost is about $5,000, and over the past 10 years, there is a decrease in the cost of solar panels. Now, in terms of financing mode, the total number in terms of total number of solar panels, there are more panels that were leased compared to direct purchase. However, if we look at the distribution by year, initially there were more panels that were directly purchased, and then the leasing options show up in recent few years, and there were more and more panels that were leased rather than purchased. Okay, and this graph is very important because it gives us the main exogenous source of variation for our identification. Basically, it shows us the distribution of, the left-hand side shows the distribution of average daily solar electricity generation per panel. So this is how it can vary in terms of daily electricity generation per panel system. And the right-hand side is the daily electricity generated per kW. So you can see even for 1 kW solar panel, you can still see a wide distribution of electricity generated per kW panel. So this variation could be due to the variation in solar radiance. It could also be due to situations such as panel quality. Okay, and then we mainly use this source of variation to identify how consumers change their gross electricity consumption in response to solar electricity generation. Yes.
What do the numbers on the x-axis indicate?
Oh yeah, so this is the kWh per kW. So this is kWh per kW generated. Yeah, daily kWh per kW. And this one is daily kWh per panel. Okay. Are there any other questions? And then we also plot very descriptively what's the average hourly electricity needed from the grid. Okay, so these are not gross consumption. Remember, gross consumption, we consider both the electricity needed from the grid and also the electricity from solar panels that is consumed by the customer. This is only the electricity needed from the grid. So you can see that for solar customers that are red curves here, they reduce dramatically the amount of electricity needed from the grid. So the message here is that even though we have rebound effects, they still generate net environmental benefit because of this reduction during peak hours of electricity needed from the grid. Okay.
That's a great question. So the blue curve is the non-solar households?
Correct.
Okay. And did you do any analysis before the installation of solar, or like any balance in the solar?
Yes, this is very descriptive graph, and then we do that in our empirical analysis.
Okay.
Great point. Okay, so related to your question, so there is indeed a systematic difference between the solar customer and non-solar customer. So this table, you don't have to read them. Basically, the key takeaway is that solar customers are more likely to have owner-occupied buildings, and then they're more likely to be on time of use pricing, have higher household income, larger square footage of their house, also more people living in the household, more likely to have a swimming pool, programmable thermostat, and also being a single-family house. Okay. And because of these systematic differences between solar and non-solar customers, that might create potential threats to our empirical analysis. So what we're doing is that we're using a combination of matching and also difference in difference analysis to correct for the systematic bias. So there are two potential threats to a causal identification of how solar electricity generation impact gross consumption. The first threat is at the extensive margin. Basically, non-solar adopters and solar adopters, as we already see, that they are completely two different group of customers. And then some of their attributes might be unobservable to us. For example, the non-solar customer might be less environmentally friendly than solar customers. And then that will also impact their consumption behavior. So we might suffer from omitted variable bias. And the second threat is on the intensive margin, meaning that after the adoption, then the factors that can impact the amount of electricity generated by solar panels can also impact their electricity consumption. For example, tree shading condition. Okay, so if you have a big tree in your backyard, that will reduce the amount of electricity generated by solar panels, but that will also reduce the amount of electricity consumed by the customers because there's lower cooling needs. And because of those potentially omitted factors that can impact both, then we can also suffer those endogeneity issues even on the intensive margin. However, so our main approach is that we use a household level time variant fixed effects to control for those unobservables. And also we demonstrate later that there is a very important assumption that holds in our paper is that when temperature is controlled for, solar irradiance only impact household electricity consumption through the amount of electricity generated by solar panels. So we're going to demonstrate, or we're going to actually test this hypothesis later after I show you the results. And that is a very important assumption in our paper that basically we're relying on exogenous variation of solar electricity generation. Again, related to your question. So we did do a matching and a balance check of our sample. So we used Corson exact matching and also propensity score matching to find a group of non-solar customers that are very similar to solar customers in the key attributes that could impact both solar panel adoption and electricity consumption. So basically the table I showed you earlier about their characteristics, those characteristics are included in our matching approach so that in the end, the solar and non-solar customers in our sample, they are very comparable to each other in terms of those attributes, such as single family house, have a swimming pool or not, time of use pricing or not, and other technology. However, the key assumption of a matching approach is that it's conditional independence, meaning that the variables that impact both solar panel adoption and the electricity consumption are observable. So this assumption is very strong and is hard to test. So in our approach, we combine this matching approach with a fixed effects panel regression in order to get rid of those unobservables. Now we also checked for balancing and common support. I'm not showing you here, but if you're interested, I can show you those balancing check and common support check later. Now, in terms of fixed effects, we use household year fixed effects to control for those unobservables, such as environmental awareness and also tree shading condition. Okay. And then for our empirical analysis, we're mainly looking at two outcome variables. The first is the daily gross consumption, meaning how much they consume both from the grid and also from the solar electricity generated by solar panels. And then in order to conduct the environmental impact evaluation, which means hourly marginal damage factor. So we're also doing the hourly analysis looking at how electricity changed hourly needed from the grid. Okay. Let's first focus on the daily level, looking at how for each consumer, their daily gross electricity consumption changes with respect to the amount of electricity generated by solar panels. Okay. And then here we control for household year fixed effects. We also control for their price plan. We also flexibly control for heating degree days and cooling degree days. Here we use spline function with 4 knots. And then we also control for holiday indicator variable, day of month indicator variable, day of week, month of year. So those are our time fixed effects. Okay, are there any questions about this regression model before I move on to talk about the results? Okay. Okay, so results from our daily gross consumption analysis. We still have this. Yeah. So this coefficient measures how consumers' gross consumption changes if there is 1 additional kilowatt hours of electricity generated from solar panels. So you can see that if there's 1 additional kilowatt hours generated from solar panel, consumers increase their gross consumption by 0.183. Means that they have 0.18 kilowatt hours additional gross consumption. And then by definition, this coefficient itself is rebound effect. The rebound effect is 18%. I know that this is different from abstract because I got the reviewer comments changing our definition. So this is actually the definition of rebound effects. So 18% of rebound effects from the residential customer on average. So in our theoretical framework, we also show that such rebound effect should be equal to price elasticity of demand. And then use our coefficient for the price variable, we can calculate the price elasticity of demand, which is equal to 0.16. So 0.16 and 18% are very similar to each other, which indirectly support what our theoretical model predicts. And then we look at how rebound effects differ by month of year. So these two graphs shows you the results from propensity score matching and coarse and exact matching. And let's focus on propensity score matching because it gives us a larger sample. And on this graph, the x-axis shows you the month of year, and the y-axis shows you the coefficient, basically that measures the rebound effect. Okay, and then this vertical line shows the 95% confidence interval. So in other words, if there you see a solid dot that's above 0, so this is the 0 line, and also if their 95% confidence interval is above 0, then that means that the rebound effects of that month is statistically significant and positive. Okay. Now, from this graph, you can see that you will see higher rebound effects during summer months, from June to October, and then you see smaller rebound effects in the winter. And then the key reason is because the electricity demand is more elastic in the summer because of large cooling needs in Arizona. So on the margin, people are using AC, meaning that they're changing their thermostats in the summer, which is relatively easy compared to in the summer, compared to in the winter. If they want to change their electricity consumption, they probably have to turn on or off of their TV or their washers, which is more difficult than just changing the thermostat setting. So in other words, the marginal demand in electricity is more, in the summer, is more elastic than in the winter, so we're seeing a higher rebound effects in the summer.
Question.
Yes.
Do you have any ideas to what percentage of total electricity demand in Arizona is air conditioning?
In the summer, it's more than half.
More than
Yeah. And then also in Arizona, in the winter, half of them use electricity for heating. Okay, so our main results use the total of the 277 solar customers in our analysis. However, here it shows you the distribution of adoption year for all of the 277 customers. And then our energy or high frequency solar consumption data is only between 2013 and 2017. So in other words, for these solar customers who adopted solar panels prior to 2013, we only have their post-adoption consumption data, the solar meter data. So in other words, for these consumers, we cannot do a real before and after or difference in difference analysis. However, there are 81 solar customers who adopt solar panels between 2013 and 2017, where we start to have energy data. And then in order to do a validity test, we do a separate matching and difference in difference analysis for these 81 solar customers, because we do have the pre-adoption and post-adoption data. Yes?
Do you know the reason for the sudden drop off in 2016?
Oh, yes. Yes. So great question. As I mentioned that they changed their net metering plan in 2014. So sometimes it took them like 1 or 2 years. So even though they applied meters around this time, but it took them 2 years to actually adopt to install the solar panels. So because of that new net metering plan, there were huge dropping panels that were installed 2 years later. There's actually another paper by a friend of mine who's analyzing how that change of that net metering plan impact solar panel adoption using a regression discontinuity design approach. Okay, then for these 81 solar customers, we plot descriptively their average monthly electricity consumption, which are shown by the red line here, compare that with the control group. So you can see that in the beginning of 2013-2014, the control and solar group, their electricity consumption profile are almost identical. But as more and more solar group actually install their panels, then they gradually increase their consumption as a group compared to their control group. So this just to confirm that they indeed share a pre-trend, okay, when there were very little solar customers.
Is the difference, is there statistical significance in the difference between consumption?
Oh, so the total consumption, I'm not testing the total consumption here. Yeah, I'm testing whether there is a difference in terms of how that changes, for example, that difference changes in response to 1 kilowatt hours of solar electricity.
Oh, okay.
So that's a great question. So we can also test whether these two are statistically significant or not. Yeah, but then for our main analysis, we're looking at solar rebound effects. So we're looking at how those difference is a function of electricity generated by solar panels, and it is statistically significant. All right, so the results show that the solar rebound effect is about 15%, slightly lower than if we use the full sample. And we also did a validity test to see whether pre-trends, they are statistically significant, different from each other, and there's no different pre-trend. Okay, basically before the solar panels adopt their before the solar customers adopt their panels, there were no difference between their consumption patterns compared to the control group. All right, so now I'm going to discuss our key identification assumptions, okay, which we got a lot of questions from the reviewers. Okay, our key causal mechanism is that we're basically use the argument from a ETO 2014 American Economic Review paper that's saying that consumers are responding to average price instead of responding to marginal price. Okay, if consumers are indeed responding to marginal price, then we should not observe any solar rebound effects because their marginal price doesn't change for solar customers. They are still paying the same price to the electric utility company. And even for the solar electricity, which is free, but in reality, they have opportunity costs. For example, if they consume the solar electricity, that means that they are foregone the amount of money that they can get from the electric utility company. So even for solar electricity, if consumers are fully rational, if they do consider opportunity costs, solar electricity is also not free to them. So in other words, if consumers indeed respond to marginal price, there should be no rebound effects. So, but we do observe rebound effects, which means that they are indeed responding to average price rather than marginal price. And we are using daily data to estimate the rebound effects. So it is very important for our results to hold so that we can say that consumers are indeed responding to average price at daily frequency. So how is that possible, right? So even sometimes consumers, it's hard for them to know that how much price they're paying at electric utility companies when they pay their bills. Then how can they respond to the fluctuations of average daily price, right? So what we're trying to say is that we find a sample of solar customer bill. And then here you can see from that sample, there is a very significant or very hard to ignore portion that shows what the total electricity consumption or gross electricity consumption by each individual solar customer, instead of just the amount of electricity that they purchase from the grid. Okay, so then because of that information, consumers can simply just use the amount of bill payment and divide that bill payment by the amount of gross electricity consumption. Okay, so and then by doing that, they will indeed find a lower average price compared to the price they paid before. Okay, they pay before they adopt solar panels, or compare those average price with different amount of solar electricity generation. Okay, if there's no such portion on their electricity bill, if they only see what they are consuming from the electric utility company, then if they divide that amount by the amount of electricity they purchase from the electric utility company, then there should be no variation in prices between the solar customer and non-solar customers. So this evidence justify our assumption that consumers are indeed can perceive a lower average price, okay, instead of just seeing the same price that they pay before and after they adopt solar panel. Okay. Any questions about this? So this might be a little bit confusing. Okay, so basically it is to show that consumers are indeed seeing their average price rather than their actual marginal price. Another key identification assumption is that consumers are attentive to daily fluctuation in average price or daily fluctuation in solar electricity generation. So indeed they can, and then these technologies basically can help them or train them to be responsive to daily fluctuations. These two graphs shows you what they can easily see from their phone app in terms of how much electricity generated from their solar panels at daily level and even hourly level. Okay? It also gives them information at daily level, what's their gross consumption and what's the amount of electricity they purchase from the grid. Okay? And then because of this easily accessible daily information, and then they can also easily perceive whether on a given day it has a lot of sunshine or not, and then they can relate the amount of sunshine level with the amount of actual solar electricity generation level. So as a result, consumers can just look at the sky and then have a perception of they have a lower average price when the day is sunny. Yes.
Do you know how many customers in your sample actually use this phone app?
That I don't know.
No.
Yes, but then yeah.
It was made aware to them that they could use
Yes.
it. Okay.
Yeah, but that's a good question. I don't know whether they actually log on into their portal or not. But then, so the idea is that they can learn this process, and then once they learn, they actually don't need to log on. They can just look at whether it's sunny or not on a given day, and then they can relate that to their amount of electricity generated. All right, so our main source of identification is how much more solar households consume on sunnier days. That's our main variation for our identification. And then it is very important to control for temperature because on sunnier days in the summer, then temperature is also higher. So consumers might have larger cooling needs and increase their consumption. Okay, so we flexibly control for temperature by using spline function of cooling degree days and heating degree days. So this is how those spline function look like. So you can see that it is a non-linear relationship. So the amount of electricity consumed per given day is increasing function non-linearly with cooling degree days and heating degree days. Okay. All right, so we further test our key hypothesis or key assumption is that when temperature is controlled for, the amount of solar electricity generated by solar panels is exogenous in our model. So in other words, solar irradiance only impact consumers' gross consumption through the amount of solar electricity generation. Okay. So in order to test that assumption, we first regress only non-solar adapters consumption on solar irradiance plus other controls, including temperature and a bunch of fixed effects and price point. Okay. And if there's no statistically significant influence of solar irradiance on non-adapters consumption while controlling for temperature and other variables, then it can justify that indeed solar irradiance does not impact consumers' electricity consumption directly. Okay. Okay, because its impact through temperature is already controlled for. And then for non-solar customers, they do not have solar electricity, so there should be no direct impact of solar irradiance on consumption. Okay. And then the second test we did is that for each non-adapter, we created a hypothetical solar electricity generation variable based on the matching results. And then also non-adapters consumption should not be impacted by those hypothetical solar electricity generation. Because they do not have solar electricity, it's just a hypothetical variable, while controlling for temperature and other variables. Okay. So we did those two tests, and then indeed there's no impact from solar radiance and also from hypothetical solar electricity generation. Okay. Okay, and then we also did a bunch of other robustness checks. Okay. The first is that we use only the post-adoption period data for only the solar customers, to avoid the concern that the solar and non-solar customer might be a completely different group, even after matching. Okay. And then with that results, we got 19% of rebound effects. Then we also removed the price variable, and it gave us 18%. We add a price variable with time of use pricing, indicator variable, and it also gave us 18% of rebound effect. We also did 2 machine learning analysis. We first used a classification regression tree-based score to find better a match group. So the advantage of that machine learning algorithm is that it can better deal with the interaction of different variables and also the non-linearity of those characteristics. And it gave us, again, 18% of rebound. And then next, we use the approach from Burley et al. In their machine learning energy efficiency paper. We basically use Lasso to predict the counterfactual of each individual consumer's electricity consumption on a given day if there were no solar panel adoption. Okay, and then that gave us 16% of solar rebound effects. Okay, so the key takeaway is that you can trust our results of 18% rebound effects. Okay. All right, so those are the results analyzing daily level gross electricity consumption. And the next, I'm going to show you the results analyzing at hourly level how solar panel adoption changed the amount of electricity needed from the grid. Okay. Now we're no longer looking at gross consumption. We're looking at how electricity grid reduced their supply of electricity because of solar panel adoption. Here I'm showing you summer and winter at hourly level. So here at x-axis is hour of day. Okay, so there are 24 such indicators on x-axis. And then y-axis is the hourly level drop in kilowatt hours delivered from the grid to the consumer. Okay. So very intuitive results. There were statistically significant drop when there were sunshine. Okay. And then just to give you some context, in the summer, the maximum hourly drop happened at 2 p.m. with 2.2 kilowatt hours per hour drop. In the winter, it happens at 1 p.m. with about 1.2 kilowatt hours per hour drop. To put things into context, for a refrigerator, on average, you use about 1 to 2 kilowatt hours per day. Then that means that the electricity that's generated by solar panel for 1 hour is more than enough for the electricity needed by a refrigerator in 1 day. However, solar electricity is not enough for the amount of electricity needed by air conditioning, okay, at hourly level. All right, the second key takeaway, or a very interesting result of this graph is that if you look at the non-solar hours, okay, when there's no sunshine, no solar irradiance, there's no electricity generated by solar panels, then there should be no drop in electricity needed from the grid. However, why we're seeing the drop of electricity needed from the grid in the evening hours in the winter month? Can you guys guess why is that the case?
Is it because of insulation?
Okay, I already showed you the answer. Okay, yes, because of insulation. Okay, so the idea, so we actually struggled with these results for a long time, and then after talking to SRP engineers, they actually told us that they checked the temperature basically above the ceiling but underneath the solar panel and compared that with the ambient air temperature. So they find that the temperature just above the ceiling during the day is lower, if the solar panel is lower than the ambient air temperature. However, if it is reversed at night in the winter, basically the temperature just above the ceiling and underneath the panel is higher than the ambient air temperature. So that means there is a reduced heating needs in the winter. And as I mentioned earlier, 50% of the households use electricity for heating. So that's why we're even seeing a drop in electricity needed from the grid during evening hours. All right, in terms of heterogeneity, for each of those 81 customers who adopted the solar panels between 2013 and 2017, we have their pre and post adoption electricity consumption data, meaning that we can do this regression analysis for each individual solar customer. And then we can get each individual solar customer's rebound effects. And then this is a distribution of the rebound effects. So you can see that there are some super large rebound customers, but there are also some of the customers that even reduce their electricity consumption if there's increasing solar electricity generation. Okay, meaning that these solar customers might be more likely to be super environmentally friendly, or they have very high environmental awareness, where they even further reduce their consumption because they adopt solar. Then to test that hypothesis, we find a zip code level voter registration data from Maricopa County. Okay, there we create a liberal indicator variable, which is measured by the number of registered Democrat voters plus the number of registered Green Party voters. Divide that by the total number of registered voters. But this is at zip code level. Then we interact this variable with the solar panel adoption variable. And then here we look at how daily net consumption or daily electricity needed from the grid is a function of these variables. You can see the interaction term is statistically significant negative. That means that for the solar customer located in more liberal zip codes, they reduce their electricity consumption more by solar customers located in relatively non-liberal neighborhoods. Yes.
Do you know how closely linked political ideology and the actual decision whether to install solar or not is linked as well?
Yes. So this paper, Kosa and Khan, they do use this indicator variable to analyze adoption decision on Prius and also solar panel. They do find positive correlation. This is one of my co-authors. That's why he suggested using this indicator variable. All right, discussion. Now back to our theoretical model, where I showed you how we can calculate the actual increase in consumer surplus. And however, because there's a debt we lost due to the fact of the difference between their perceived price and the actual price, then the actual consumer surplus is $972 per year. Okay, so this is increasing consumer surplus because they adopt solar panels. And then we can get this number because we estimate empirically what's the rebound effects, and then because that is equal to price elasticity of demand, then we can plug that number back to our demand curve and then calculate the consumer surplus change, which is about $972 per year. Okay, so that is basically how happier consumer each solar customer are after they adopt solar panel. Okay, and then on average, I showed you that without considering any financial subsidy, per panel costs the consumer about $34,000. Okay, and if we use the annual increase in consumer surplus to calculate the payback period by dividing this cost by the consumer surplus, increase in consumer surplus, then the payback period is 35 years. Okay, which is very long. Okay, without any financial subsidy. And then if there's no rebound effect, then this part is just the amount of the amount of increasing consumer surplus. So ignoring rebound effects can miscalculate the increasing consumer surplus by 12%. Yes.
When you were looking at the payback period, were you including any assumptions about the lifespan of the panels?
No, so basically assume you're absolutely right. The panel only lasts for 10 years and 15 years, then there's no point of 35 years payback. So we're not restricting any assumption on that.
Where's the payback period, assuming no rebound effect?
Great point. Okay. I think it's in the paper, but I don't show it here. Basically, the rebound effect will be shorter because the actual change in consumer surplus, there's no debt we lost over there.
Okay. So I guess I'm interested in going back to the motivation to invest in solar. I imagine that I don't know what those net energy metering policies are at this other project, but they don't look that great from an economic standpoint. So maybe the motivation to install those are more ideological or environmental rather than economic.
So because you're
in DC, we have much richer incentives to install solar, so maybe the motivation is different and that can also affect.
When you say more incentives in DC, you're saying the net meter price or other financial subsidies?
Net metering or SREC market, I imagine is much higher.
So I would say that this net metering policy in Arizona is actually quite good because it values the retail, values the electricity at retail rate. Okay, so there are some other electricity utility companies, they only value the solar electricity at wholesale rate. Yeah, so I think the problem is more about other type of subsidies rather than net metering itself. But then, or it could be the electricity prices in Arizona are lower than electricity prices here. Yeah.
So I know subsidies weren't included in the analysis, but just out of curiosity, do you know what kind of subsidies or out-of-market incentives there are in Arizona?
So they can definitely be qualified for those federal level subsidies, such as ITC investment tax credit or production tax credit. Depends on the size. At Arizona level, actually, I haven't done the research. They probably have some utility level rebates that they can obtain. But I would say that utility probably hate to give rebates to solar customers because of the reason I mentioned earlier. They have to cover their upfront costs, and then basically they're not paying them enough. But still, they're using a portion of the grid. They're not reducing their maximum demand, but then they're only reducing their payments. All right, now with the hourly level results, and then also with the, so these two graphs, we're already seeing it in previous slides. And then, so these are the marginal damage factor from 4 major pollutants from, again, another AER paper from Holland et al. They basically give for each ERCOT region, I'm only using Western Electricity Coordination Council where Arizona is located, for each major pollutant, what's their monetary damage at any given hour of day, okay? And then we can multiply the marginal damage factor for each of the pollutants for a given hour by the amount of actual reduction in electricity needed from the grid, okay? Then that will be the environmental benefit from solar panel after considering rebound effects, okay? So if we do not consider rebound effects, we can just simply use these marginal damage factor, multiply these by the amount of electricity generated by solar panel, and that will be the environmental benefit. But then we are multiply these by the amount of actual reduction in electricity, hourly electricity needed from the grid, and that is considering rebound effects. And then after those calculations, the total environmental benefit from carbon dioxide, sulfur dioxide, NOx, and particulate matter in total is about $178 per year per customer. Okay. Which is not a big number, right? So the environmental benefit of a solar panel system after considering rebound effects is $178 in Arizona. So if we ignore rebound effects, basically do the simple calculation as what most existing studies are doing, multiply the marginal damage factor by the amount of electricity generated by solar panel, that gives us so these are $2,000, okay, the year $2,000. So that's why it looks different from the previous slide. But then the key takeaway is that if we look at $2,000 year dollar, without considering rebound effects, the environmental benefit is $162. Compared to $122 after considering rebound effects. So without considering rebound effect, we'll overestimate the environmental benefit from solar panels. All right, so as I discussed earlier, there has been a lot of discussion of rebound effects in energy efficiency literature. And what they're finding is that in developed countries, direct rebound effects range from 9 to 12%. And our indirect rebound effects from solar panel adoption is 18%. Okay, comparable but higher because we're looking at indirect rebound. All right, to summarize, here are our policy implications. We basically show that the magnitude of solar rebound effects are important. And if we ignore solar rebound effect, it can change the policymakers' evaluation of many types of potential benefits and costs of solar panels. For example, you could ignore rebound effect, will miscalculate the amount of increase in consumer surplus, will overestimate the environmental benefit. You will also have huge implication in terms of accounting for distributed solar panel to meet the renewable portfolio standard. This is because of rebound effects. It will make the distributed solar panel harder to help states to meet renewable portfolio standards. Now, in terms of distributional impact that we discussed earlier, basically, rich people are adopting solar panels, and the non-solar panel adopters are subsidizing the rich. Okay. For that discussion, we showed that rebound effects should be considered when designing the new rates that address that equity issues. Okay, because now we're seeing that solar customers actually increase their consumption. Okay. All right, and then all these discussions are important because currently they're in most of the integrated assessment model and in most of the economic assessment model, there's no consideration of solar effects. All right, some other three last policy implications. Our estimated payback period is without any financial subsidies more than 30 years, which is very long. So cost of solar panel installation should continue to go down, or we should continue to rely on subsidy for it to be actually attractive. And then we'll also show that lifetime environmental benefit is about 2,600 to 3,400, depending on whether the lifetime is 20 to 25 years. And then because these are positive externalities generated by solar panels, then that means that the financial subsidies should be at least this amount. Okay. And then lastly, we show that we can use a very nice exogenous variation of solar electricity to help us estimate the price elasticity of solar customers, which can also be applied to non-solar customers. So our results have also important implications for policymakers to evaluate any other type of policy that can impact electricity prices. Okay. Great. Thank you. That's the end of the residential part. Thanks. Are there any questions about residential part before I move on to business? Or I should only have a few slides on business.
Yeah, that's fine. I do have a question. So based on this, is there a case for subsidizing distributed solar? Why shouldn't, how about just giving all the money to grid scale solar so that there won't be any rebound effects?
Oh, okay, so no distributed solar, right? Just that's a great point. So that means that there should be more policy incentive for grid scale instead of distributed scale.
So I'm just thinking that distributed is much more expensive than grid right now, and based on your results, distributed also has this significant downside of a rebound, which presumably would not happen with grid scale because it just goes into the price.
Yeah, so for grid scale, again, so that will make the rate. So I understand your point. I think will be more costly for the electric utilities, so the rates will still be much higher than electricity from natural gas power plants or coal power plants. But versus for residential customers, because solar electricity value at retail rate might be more financially attractive to them compared to how attractive it is. So basically how attractive it is, the distributed solar panel to residential customers compared to how attractive it is, the grid scale sort of solar farms to electric utility companies.
That's what I think. From the social perspective, I don't think it matters a whole lot. Sort of, you can always play with the incidence of the benefits with all kinds of additional instruments. I'm just thinking that from this, I'm learning that distributed solar is worse than I thought.
Yes.
Is that correct?
Correct. Yeah.
Perhaps I guess more question on your questions than about the presentation. But would there be, if there is a rebound effect from grid scale solar, would it be different than what we see with wind? And also, I guess the second part of that, has anyone tried to quantify whether consumers knowing that they're getting electricity from, say, wind would have increased consumption? I don't know. Just kind of.
Well, I'll just pass the question on to Lucy. So what do you think? You add significant amounts of renewable to the grid. Can you get still some kind of a rebound? Or
so if consumers are rational, then no, because they do not see their average price to drop. They're still paying the same amount of bills. So if they're rational, then no. But then if they are thinking that that's called there's actually a term for this, that if they're doing one thing correct, then they can do some other things that are wrong, right? I don't know what's that called. Basically, there's
Single action bias. Yeah.
I forgot, but there's a term in psychology, basically because they know that now the electricity grid is cleaner, then they can use more electricity. That's actually a great research question.
Well, anyone who's ever tried a diet can probably identify with that.
Yeah.
Point.
Yeah.
You know, I ate healthy all week. I can go eat some cake now or whatever.
Yeah. So a fully economically rational consumer will have no change. Yeah.
Cognitive dissonance.
Yeah.
Yeah.
I single action
Bias. That's what it's
Single
called,
action
yeah.
bias.
That
That's
would
right.
be, I think it would be really fascinating to see, to quantify the single action bias differential between rooftop solar and community solar. Because there's a lot of kind of behavioral feedback of seeing the panels on your physical roof rather than having them somewhere else in your community.
Yes, and the community solar is nowadays a big thing. Yeah, and that's our next step, is to get more data about community solar customers and evaluate whether rebound effects are different.
Yeah.
Good point.
So I work for the DC government, and we just passed a law where we're going to attempt to get 10% of our generation from solar generated in the district by 2041. So this study has material impacts on kind of how we're going to go about, probably how we should go about doing our load forecasting, for example, with a lot of distributed solar in the district. I know that there are applications of behavioral science in the energy efficiency space to counteract this, or to help improve conservation and counteract some of the rebound effect. Do you see more applications for solar?
No, yeah, because even the solar rebound effects, this concept itself is quite new. Yeah, I don't see a lot of behavior, for example, O-power type of nudging stuff. Yeah, I don't see
I
that.
used to work for O-power.
Oh, great, good
So,
for you. Okay.
Why do you think that nudging would be less effective?
Oh, I'm not saying nudging will be less effective. It's just I haven't seen any nudging conducted for a solar panel, solely for them not to have rebound.
The paper is not yet published. Once it comes out and people realize this problem, then
I'll
all
forward
the
it to my
consultants will
Great,
former
thank you.
colleagues.
Yeah.
So we're just waiting for
We're now
the big announcement.
addressing reviewer comments,
That's right.
which I think are addressable. Yeah.
Great.
Wonderful.
Yes.
So, no, I was just, I'm just saying, in the interest of that, we have another 10 minutes, so if you have slides to go through.
Yeah, I would like to hear James.
Let's get James comment
Yeah,
first.
yeah,
and
yeah,
then
I'm just
we
gonna
will-
build on what Johannes was saying. I think it's the mechanism is different when you have household solar versus community or utility solar.
Yeah.
And it's almost this very political issue where the politicians say, well, we made these rebates available. This is a very popular program. We have this to point to. Whereas when you're pumping money into rebates at the utility level, no one sees those.
Right.
And so from a political perspective, it just doesn't serve the same purpose.
Yeah.
So I think that in particular, like one might make more sense, but when does that ever matter for politics?
Do you have any comments on that comment?
Seems to make a lot of sense.
Not to be too cynical.
Well, but it is certainly true. I mean, you know, this is an economist. If you look at any kind of renewable energy subsidy or something, they're usually very far from any kind of optimal or efficient. They really, clearly there's some very complex multi-dimensional problem that informs what goes into these policies. And I think the visibility part is very important. Is that you said that if you have your own panel churning out kilowatt hours, it feels very different from. I have 100% renewables through some kind of credit arrangement, but it's so remote from where I am what I actually do that I'm having a hard time imagining if there's any impact on my behavior. But if I had my own little panel producing kilowatt hours, that might make me, let me go and have a steak or something.
You're probably paying a premium for that clean
But it's
electricity.
very small, yes.
So you may be experiencing
the opposite. That's right.
Price.
Well, I have to say, I made a smart move when when we bought our condo. We bought a very sort of modern and efficient one. So my electricity bill is actually super low. I pay usually something like $20 or something. So it's so small that I'm probably ignoring mostly what's happening.
In Arizona, it's at least 400 in the summer.
Monthly.
Yeah, monthly.
It's a lot.
Not quarterly.
It's a lot more than that.
Yeah. Okay.
Anyway, please do
to
show
quickly
us
show you
some
business
business
results.
what's interesting
Basically,
in business.
okay, so if you are into the energy literature, you will see that a lot of the consumer behavior stuff is only focused on residential. And then part of the research is to look at business customers, basically non-residential customers. And they're important because they're responsible for 62% of total electricity in the US and also 63% worldwide. Okay, and then also in terms of distributed solar customer, the non-residential customer and the residential solar customer are very comparable. So we should not just focus on analyzing residential customer. Yeah, so basically there's a lack of empirical studies on non-residential customers. Okay, again, very similar pattern, higher rebound in the summer compared to in the winter. And we got the data of more than 300 business distributed solar customers. These are like firms. They have, for example, a solar panel garage, or they have solar panels on their rooftop. Okay, and then we also have 17,000 non-solar business customers to choose from to construct control group. Okay, but so the results are actually surprising and very unbelievable. Is that their rebound are huge. Instead of 18%, 80%. Okay, so we're going to do more analysis basically, but then there is one study that support our results is that they do find business customers are more price elastic. Then their price elasticity can be very high, like 0.8, which is exactly can be translated into 80% rebound. Okay, so these are not fully. At least to show that these results could be correct. Okay. So this graph is not about rebound, but this graph is about how adopting solar can impact their maximum monthly electricity demand. Okay. Remember that electric utility company, they have to provide sufficient infrastructure, transmission, distribution, and also they have to purchase enough electricity, or they have to build enough power plants to just meet the peak demand. Okay, they're not sizing their infrastructure based on average demand, but based on peak demand, which normally happen in Arizona in July and August. Okay, so you can see that adopting solar panel does not reduce their peak demand at all. Okay, then even though they reduce their peak demand in non-summer hours, but not in non-summer months, but then their annual total peak demand doesn't change. Then that means that adopting solar panels will not cause the electric utility companies to reduce their infrastructure investment. Okay, so that further illustrates that demand charge is very important for electric utility to address the problem of the mismatch between reduced revenue, but and with the non-changing infrastructure need. Okay. And this is actually a very key important message of our business paper, is that even though revenue reduced, but then infrastructure need doesn't change. So this, you already know this. Basically, this is hourly results, very similar to residential. Okay. And this is to illustrate that, again, so these are the hourly actual solar generation. These are the hourly reduction of electricity needed from the grid. So if ignoring rebound effect, okay, you can see that we can overestimate the environmental benefit by just using the solar electricity generation. All right, so that's really the end of my presentation.
Okay.
Thank you. Yeah. Thank you.
Any final questions from the audience?
Thank you. Thank you for those comments.
All right, wonderful. This was very, very interesting. And as I said, you made history for our program.
Is it recorded somewhere?
Yes, it will be recorded as well, and you can go on and see it. But thanks so much for coming. This is really, really interesting. We are now a bit ahead of the curve. We know about the Rebound, and the DC government is going to take action to deal with the problem. So you had a huge policy impact by coming here. So we're all very grateful for that. Thank you very much.
I'm just gonna say, it seems like very important work. So
thank you.
thanks for it.
Yeah. Do you have a business?
I do.
Okay.
All right, live streamers, we are pretty much done here. Thanks for your attention, and see you next time.